Hey everyone. In some of these testing physics video series, I've been using these motion sensors, and in the comments and in other discussions, the question has been brought up of how accurate are these sensors, especially when we are aiming the sensors at each other. Are these making reliable measurements? Which is a fair enough question. So what we're going to do in this video is test out these motion sensors and measure how accurately are they able to measure distances, how accurately are they able to measure velocities, and when these sensors are aimed at each other, can we detect when they're giving reliable data or if they're kind of interfering with each other. So to get started, let's talk just a little bit about how these motion sensors work. So these motion sensors will send out pulses of ultrasound. So they send out this pulse of ultrasound, and that will move through the air and then hit our target. The sound is reflected backwards, and the detector picks up when that echo of that ultrasound pulse arrives back at the detector. And if we know the speed of sound in ordinary room temperature air is around 343 meters per second. So if we know that velocity and we know how long it took that pulse to go from the detector to the object we're tracking back to the detector, we can measure the distance for that. And if I have the distance and I know when the object was at that particular distance, if these objects are moving, we can figure out, well, how is that distance changing with time? So that can give us velocity. If we know the velocity at different times, we can measure the acceleration from that data. But all of that data is based off the distance measurements from the sensor to the objects that we're looking at. So we're going to be testing out how these work, and when these two sensors are again aimed at each other and they're both sending out ultrasound pulses, can they interfere with each other? And again, can we detect when they are interfering with each other? So a couple of things that I want to mention on here. I've put little markers on this track at 10 centimeter intervals. So let me move the camera so you can see this a bit better. So at the 30 centimeter mark, at the 40 centimeter mark, 50, 60, 70, 80, and 90, I've put these little markers so we can actually track with the video how far are they going in a certain amount of time. So that's going to be some of our checks for, are we actually measuring positions? And the way that I have set up these sensors is that when the middle of these two carts are at this point, both of the sensors will measure this as this is going to be position 0, and both are saying to the camera's right is going to be the positive direction. So I'm going to change my camera around a little bit so you can see this a little bit better, and so we can also see the graphs that are being produced. So let's put this system to the test. Our first test is focused on how these motion sensors measure positions. And we're going to test that by moving these carts to different known locations on the track and seeing what the motion sensors measure. These arrows that I've put on here are again 10 centimeters or 0.1 meters apart each. And I've set up the sensors so both sensors should read this location. When the sensors of the carts are at this location, that should be the 0 point. So when the carts are here, both sensors should read 0.1 meters, 0.2 meters, 0.3, 0.4, 0.5, and 0.6 meters. So that's what we're going to be testing, but let me emphasize this right at the beginning. I fully expect that there are going to be points where we're not getting good tracking from both sensors simultaneously. What's important is whether we can identify from the data when there's bad tracking in the sensors. So that if we're doing an experiment, we can either take another data run to make sure that we are actually getting good tracking. And if we see these telltale signs of bad tracking, make sure that we don't include that data in any analysis that we run based on that experiment. So again, one of the things that we're really going to be trying to emphasize is how do we tell when we are getting bad tracking from one or both of these sensors. Okay. So let's start with this, let's say in the middle, so at the 0.3 meter mark, so that's where the center of those carts should be. And let's start taking some data. Okay. So both sensors seem to be reading 0.3 meters. We're getting 0 velocity. Everything looks good so far. Let's move this back to 0.2 meters. Okay, both sensors are reading 0.2 meters. Everything looks good. Going back to 0.1 meters. Everything looks good. And when we go to 0, well, I'm kind of surprised. Everything's still looking good. So let's go in the other direction. So we can move both of these up. And now, oh, we started getting some bad tracking. So if I move this to 0.4 meters, notice that position sensor 1 is still getting good tracking, but position sensor 2, that one's starting to drift. But our telltale sign is looking at this velocity data. The blue sensor, the position velocity 1 data, that one is very stable, but the red one, the one that's drifting, we're getting very, very noisy velocity data. And that is going to be our sign that bad tracking is occurring. If I move this to another location, let's say to the 0.5 meter mark, notice position sensor 1 is still tracking well. Position sensor 2, no, definitely not working for position sensor 2. If I move this to 0.6 meters, again, position sensor 1 is tracking well, position sensor 2 isn't working out as well. So let me stop that one for now. Again, the thing that I want to emphasize is we can identify when bad tracking is occurring because when we were getting good tracking, that velocity data was very, very stable. It had low levels of noise. As soon as we started getting that bad tracking, well, that velocity data becomes much, much more noisy. So if we see these signs of very noisy velocity data, we can identify, well, it might not be tracking very well. That's not going to be a reliable measurement. So we're not going to include that data. And very, very often, that mistracked data is going to be very noisy and also centered around 0. If the cart's moving at some larger velocity, we're going to be able to tell when that tracking is not working because that velocity data will be really noisy and centered around something at 0 or very close to 0. But if we turn this sensor back on again, so let's see if we can get some good data again. So now both are being tracked, and at least in this region here, if I zoom in on this data, at least in this region over here, it's tracking both of the carts quite well. So when I do an experiment, I want to make sure I identify, if I go a little bit too far to the side, sensor 2 is not tracking anymore. If I go a little too far to this side, well, now sensor 1 is not tracking very well. But if I have this kind of intermediate range, we can say that, oh, that data is going to be much more reliable. And again, when we're getting that good tracking, that velocity data is far, far less noisy. For example, when the sensor 2, the red one, was not tracking in this section here, notice that that velocity data becomes hugely noisy. So that's going to be our way of identifying when we are losing tracking on one of those carts. And again, we can either take another data run to try to avoid, make sure we're staying in that range where we're getting good data. And maybe we'll get better tracking on a separate trial, or we can just make sure that our analysis does not include those sections where we're getting noisy data. So next, let's play around with how do we measure velocities from both of these carts. So what we're going to test next is how do these sensors do at measuring velocity. So we're going to test that by me giving this cart a push. And based on these position measurements, again, each one of these is 0.1 meters, so the whole length from here to here is 0.6 meters. I'm going to time how long does it take the center of the cart to go from this point over to this point. And if I know that if I know that time and that distance, I can measure the velocity, and we're going to compare that against what the motion sensors are saying is the velocity. We're also going to, again, try to check out if I can just use this velocity data to identify when we have good tracking and when we don't have good tracking. Remember, when we don't have good tracking, this velocity data looks much, much more noisy. So I'm going to hide the position data, and then see, based on this velocity data, can we predict where that tracking is messing up a little bit? When do we get reliable tracking? Because in later experiments, we're going to be basing our interpretation of when we're getting good data and when we're getting bad data based on how noisy this velocity data is. So when I'm timing these pushes, I'm going to be using a stopwatch to measure these times, but my ability to measure times with a stopwatch isn't going to be super great. So when I do each of these trials in post, I'm going to add in a timer onto here that's going to look at this frame by frame, and we're going to use that to also identify, start the timer right when the cart is reaching this first mark right here, and stopping the timer right when it passes that second mark. And in the editing, I'll add in what the results of those particular measurements are. So let's try one of these measurements. So I'm going to start with just a relatively slow push for this thing. And we also want to make sure that we are running the motion sensor at the same time. So again, I'm going to start the stopwatch right when the center of the carts is at this point, and then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 meters later, that's when I'm going to try to stop the stopwatch. So we'll start out with a slow speed, so I'll turn on the sensor, give this a push. And let's see what we got. Okay. First off, for this data, my stopwatch time was 3.43 seconds. So we've got seconds in the bottom here, so 3 seconds, 0.34 seconds. So if I take 0.6 meters and divide that by 3.34 seconds, so again, that was 3.34 seconds, the velocity during that motion, during that average motion, should be around 0.18 meters per second. So when I plug that in, I got 1796 meters per second, so about 1.8 meters per second. Let's compare that with what we got when both carts were being tracked. Now, notice that the carts were slowing down a little bit, but right in here, where our data isn't very noisy, it looks like we're getting good tracking on both of the carts. So let's check that against our motion data. Yep, those seem to have good tracking on both of the carts during that point. Earlier on, again, we had noisy data and it was not actually tracking cart number 1. Later on, we're not tracking cart number 2, but we get this noisy section of data. Right in here, we've got good tracking on both of those carts. So if I look at the statistics for this, notice both of these are at 0.189, right around 0.189 meters per second. And from me timing this by hand, I got 0.180 meters per second. Again, my ability to time this super accurately with just a stopwatch is going to be very limited. I would not expect to be, I'd expect at least like 10% error for measuring times that are relatively short like that. Okay. So this one seems to match up, and again, I'll put up top what the results are from actually doing the video analysis part, but let's try another example. So I'm going to close these ones. Good. And this time I'm going to give it a little bit more velocity when I give this a throw. So let me reset my stopwatch. Pull this back over here. Let's do another case where I give this a little bit more velocity right at the beginning. So here we go, starting the sensor and giving a throw. Okay. So that one, my time there was 2.09 seconds. So again, trying to get that showing up as well as it will on the camera. 2.09 seconds to go 0.6 meters. So that measured value would be 0.6 divided by 2.09. I got 0.287 for that velocity during that run. Okay. Well, again, we can identify based on, oh, there's not very much noise in this velocity data, that this is when we have good tracking of both of those carts. And when I look at the statistics for this, the statistics on both of those, again, my value is 0.287 meters per second. This is 0.282, 0.281, in very good agreement with each other. And again, one of the things that I really want to emphasize is we can identify from the data when we're getting good tracking or when our tracking is a little bit off. Let me do one more example of this just for good measure. So I'll try a little bit of a higher velocity, a little bit of a faster push. So resetting one more time. And we will start the sensors. And here we go. 3, 2, 1. That wasn't very fast. Let me try that one more time. Here, let me reset that. I didn't push that fast enough at the beginning. So here we go. So 3, 2, 1. Okay, that one I doubt that I timed super well. Let's change the scale of that graph. I got 1.34 seconds. So again, 1.34 seconds. And if that went 0.6 meters in 1.34 seconds, that should be 0.448 meters per second. Again, I think I might have been a little bit early on hitting the button. I don't think that my timing is reliable. Again, I will put a timer in post. You should already be able to see what the actual time was from that analysis of the video. But from this data, if I look at this velocity data, the average velocity for those is 0.405, 0.406 meters per second. And again, I don't have the numbers right now, but I will definitely put this in post, how close these measured values from the sensors are compared to what we get from the video analysis. Also notice that there is a little bit of friction on this track, so this velocity is changing a little bit. This part right here looks like it's closer to the end of our motion, but again, hopefully these will be in pretty good agreement with each other. So the things that I wanted to kind of end off this video on. When we are using these sensors, we do have to be careful to make sure that, especially in cases where I have two sensors aimed at each other, that we're getting good tracking on both of the objects, especially when we're dealing with things like collisions. But we can identify when our sensors are not tracking properly based on how noisy is the data from the velocities. Okay? If I see very noisy velocity data, it's a very strong indication that we're not getting good tracking. When I have very stable data from that motion for that velocity, well, that's a good sign that the tracking is acting very, very accurately, or at least sufficiently accurately for our purposes. Again, these aren't the absolute best motion sensors that have ever been produced, but they meet the needs, and we can identify what kind of levels of error we're having in here. Again, I will make sure to put in post, well, what percent off are our two different ways of measuring these velocities. So when we are looking at different experiments with these, we can identify when we are getting noisy data, and that allows us to make informed decisions on what data to use, when to redo trials to try to get cleaner looking data. And one last thing that I want to mention is when we are looking at the results, let's say our sensors were not working reliably, just giving weird, different values for the velocity than what they actually are. If we analyze that data, and let's say it supports some of our ideas on conservation of momentum, or conservation of energy, or accelerated motion, whatever sort of system we're looking at, if we include data that is inaccurate, it's very, very unlikely that just by chance we would get a close agreement with some proposed model. You know, if we're doing a conservation of momentum experiment and we see that, momentum is conserved, if the sensors were just giving us really, really bad data, it would be exceedingly unlikely that the numbers would work out. The sensors would be working incorrectly, but incorrectly in just the right way to have us match up with a particular model and have us match up with that particular model over multiple trials under multiple different conditions. Having the sensors work wrong in that kind of way would be exceedingly unlikely. So again, these sensors, even when we're using them in this way where they're facing each other, we can identify when our data is noisy. We can identify when the tracking seems to be pretty good, and in those cases where the tracking is working, we're getting reliable measurements for positions, velocities. If I know how the velocity is changing, I can calculate the acceleration. We can have a fairly high level of confidence in when these sensors are working and when these sensors are not working. And again, when they're not working, we can take different data runs and redo those parts of the experiment. So again, I hope I've made a case. One other last thing, sorry, I'm having multiple last things here. This is the worst case scenario. When I have collisions, and let's say the carts are not directly beside each other, when those carts are closer to their respective sensors, it's going to increase the likelihood of good tracking, because those carts are going to basically be closer to the sensors, closer to their respective sensors. So it's much more likely that this one is going to accurately pick up its motion, because this one over here is blocking that sensor's signal, and this one is getting a much more direct signal from its sensor. So the case that we've done with having these two carts stuck together, that's kind of like the worst case scenario, and we are still able to find reliable data from this. So hopefully that addresses any concerns that these sensors are just randomly doing things completely off, and that we have no way of knowing when we're getting reliable data from these sensors, because I'm going to be continuing to use these sensors in a number of different experiments. So we want to make sure that any instrument that we're using has a high level of reliability. So that's it for this one. Again, we'll be using these sensors for a variety of different experiments. So hopefully this is good to just kind of go through these checks to make sure everything's working. As always, if you have questions, throw them into the comments. If you have suggestions for other videos or things that we can do, please let me know. And thank you for your attention.